Hello everyone and welcome. I'm excited to have you here today. We're about to dive into the fascinating world of machine learning. The title of our presentation is Introduction to Machine Learning, and we'll explore what it is, how it works, and why it matters. Over the next few slides, we'll cover the basics, some key concepts, and real-world applications. So let's get started and discover the exciting potential of machine learning together. Machine learning is all about programming computers to optimize a performance criterion, and we do this by using example data or past experience. Unlike traditional programming, where you write explicit instructions, here we let the computer learn from data. For example, there's no need to teach a computer how to calculate payroll. It knows exactly what to do without learning. We use learning when human expertise isn't available, like navigating a rover on Mars, where no one is around to guide it. It's also useful when humans can't easily explain their expertise, such as in speech recognition, where the system learns to understand spoken words without explicit instructions. Learning is essential when the solution changes over time, like routing data through a computer network where conditions are always shifting. And it's necessary when solutions need to adapt to specific cases, such as recognizing individual user biometrics, like fingerprints or facial features. So the key idea is that learning allows computers to fill in gaps where human knowledge is limited or dynamic. It's a powerful approach that helps us solve complex problems that traditional programming just can't handle easily. Let's talk about learning general models from specific examples. You see, data is usually cheap and easy to get. Think of data warehouses and data marts, while knowledge, on the other hand, tends to be expensive and hard to acquire. For example, in retail, we might look at customer transactions to understand consumer behavior. A common insight is that people who buy the Da Vinci Code often also buy the 5 people you meet in heaven. This kind of pattern helps us build models that are good approximations of the data, meaning they capture useful information without needing every detail. When we say learning, we're talking about creating models that reflect the underlying patterns in data in a way that's helpful and practical. So, in this context, learning is about turning specific examples into general knowledge that we can apply to new cases. Now, let's look at some of the key applications of KDD across various fields. As Fayed describes, KDD is essentially the non-trivial process of discovering valid, novel, potentially useful, and ultimately understandable patterns in data. It's not just about finding any pattern, but about uncovering meaningful insights that can be acted upon. In retail, for example, KDD is used for market basket analysis, helping identify which products are frequently bought together, and for customer relationship management, or CRM, to better understand customer behavior and improve service. In finance, applications like credit scoring help assess the risk of lending to individuals, while fraud detection is crucial for spotting suspicious activities and preventing theft. Manufacturing benefits from KDD through optimization, making processes more efficient, and troubleshooting by diagnosing issues before they escalate. In the medical field, KDD supports medical diagnosis by analyzing patient data to identify patterns that can lead to earlier and more accurate diagnoses. Telecommunications uses KDD to optimize the quality of service, ensuring network resources are allocated efficiently and service interruptions are minimized. Bioinformatics applies it to find motifs and perform sequence alignment, which are fundamental for understanding biological data. Web mining leverages KDD for search engines, improving search results and user experience by analyzing web data. As you can see, these diverse applications all revolve around the core idea of extracting valuable knowledge from data, which is central to the overall theme of our presentation. Let's take a closer look at what machine learning really involves. Essentially, it's the study of algorithms that get better at performing a specific task over time, based on experience. Imagine how we learn from past data or previous attempts. That's exactly what these algorithms do. They optimize a performance measure by analyzing example data or past experiences to improve their accuracy or efficiency. Now, when we talk about the role of statistics here, it's all about making inferences from a sample. That means using a subset of data to understand and predict the broader picture. On the other hand, computer science plays a crucial role in making this process efficient. It develops algorithms that can solve the underlying optimization problems quickly and effectively. This includes representing the model, which is how we formalize our understanding, and evaluating it to ensure it makes accurate inferences. So, in summary, machine learning combines statistical inference with computational efficiency to create systems that learn and improve from experience. Today, we're looking at how machine learning has become the preferred approach across a wide range of fields. For example, in speech recognition and natural language processing, machine learning enables more accurate and flexible understanding of human language. In computer vision, it allows computers to interpret and analyze images and videos effectively. Medical outcomes analysis benefits from machine learning by helping identify patterns and predict patient results more precisely. Robot control is also advancing rapidly, making robots more autonomous and adaptable. When it comes to computational biology, machine learning helps in understanding complex biological data and processes. What's really interesting is that this trend is accelerating. Improvements in algorithms, along with better data capture, faster computers, and enhanced networking, are all contributing to this rapid growth. Software development has become incredibly complex. It's no longer feasible to write everything by hand, which pushes us towards machine learning solutions. Additionally, the advent of new sensors and input-output devices expands the possibilities for data collection and application. There's also a growing demand for systems that can be self-customized to suit individual users and environments, adding another layer of complexity and opportunity. However, it's worth noting that extracting knowledge directly from human experts has proven to be quite challenging, which partly explains why expert systems in the 1980s didn't meet expectations. Overall, the growth of machine learning reflects a fundamental shift in how we approach problem-solving across many domains, making it an essential part of modern technology development. Let's take a closer look at association analysis, which is a key part of supervised learning. This involves techniques like classification and regression or prediction, where we use labeled data to train models that can categorize data points or forecast future outcomes. On the other hand, we have unsupervised learning, where the data isn't labeled, and the goal is to find hidden patterns or groupings within the data itself. Then there's reinforcement learning, which is quite different. Here, an agent learns by interacting with an environment, receiving feedback in the form of rewards or penalties to improve its decision-making over time. All of these methods have a wide range of applications across industries, from customer segmentation and recommendation systems to predictive maintenance and autonomous vehicles. Understanding these different learning types helps us choose the right approach for solving specific problems, which is a vital part of our overall data science toolkit. Let's talk about market basket transactions. This is all about understanding what customers tend to buy together. We use something called basket analysis, which helps us identify these buying patterns. In essence, we look at the probability that if someone buys product X, they will also buy product Y. We denote this as P, YX. So, it's the probability of Y given X. It's a way to see how products are associated with each other in the shopping cart. For example, imagine the probability that someone who buys chips also buys beer. We might find that P, chips beer, equals 0.7. That means there's a 70% chance that a person who buys beer will also pick up chips. This kind of analysis is very powerful because it helps us learn associations between products. These insights can be used to improve cross-selling strategies, optimize product placements, or even develop targeted promotions. By understanding these relationships, we can better tailor our marketing efforts to customer behavior, making shopping experiences more personalized and effective. So, Learning these associations is a key part of leveraging data to drive smarter business decisions. In this slide, we're looking at a simple discriminant model that helps us classify data points based on certain conditions. The model states that if a person's income is greater than a threshold θ1 and their savings are greater than another threshold θ2, then we classify them as low risk. Otherwise, they are considered high risk. Think of this as a decision rule that uses these two variables, income and savings, to make a quick judgment about risk level. For example, in credit scoring, this approach can help us differentiate between low-risk and high-risk customers by analyzing their income and savings patterns. The core idea here is classification, using specific criteria to sort data into categories. This model is quite straightforward but powerful because it allows us to make decisions based on multiple factors simultaneously, aligning with our overall goal of effective risk assessment. Let's delve into some key applications of pattern recognition. When it comes to face recognition, it's not just about identifying a face, but also accounting for variables like pose, lighting conditions, and occlusions, things like glasses, beards, makeup, or hairstyles that can change how a face appears. Similarly, character recognition involves understanding different handwriting styles, which can vary greatly from person to person. This is crucial for digitizing handwritten documents accurately. Speech recognition, on the other hand, relies heavily on temporal dependency, meaning it considers the sequence of sounds over time to interpret what's being said. It also benefits from using dictionaries or the syntax of the language to improve accuracy, ensuring the system understands not just individual words, but the context as well. Sensor fusion is another fascinating area, combining multiple modalities, like visual cues such as lip images with acoustic signals, to enhance speech recognition accuracy. By integrating different sources of information, we make our systems more robust. In medical diagnosis, pattern recognition helps clinicians move from identifying symptoms to pinpointing specific illnesses, enabling earlier and more accurate diagnoses. And in web advertising, pattern recognition is used to predict whether a user will click on an ad, allowing for more targeted and effective marketing strategies. All of these examples highlight the versatility and importance of pattern recognition across various applications, connecting back to our overall theme of how intelligent systems interpret complex data to make informed decisions. Let's take a closer look at some of the resources we've been working with. Here, we have a reference from AT&T Laboratories in Cambridge, UK. If you're interested, you can visit their website at the URL shown on the slide. They've compiled a database of face images that's widely used for research purposes. On the slide, you'll see test images. These are examples of new faces that our system hasn't seen before. They help us evaluate how well our face recognition algorithms perform in real-world scenarios. Next, we have training examples of a person. These are the images used to teach the system what a particular individual's face looks like. The more diverse and representative these training examples are, the better the system can recognize that person later on. Overall, this slide highlights the importance of both training data and testing data in developing effective face recognition systems. It shows how researchers use real datasets to train algorithms and then test their accuracy with new, unseen images, an essential process for building reliable biometric identification systems. Let's dive into this slide. The equation y equals wx plus w0 is a simple way to represent a linear relationship. Think of y as the outcome we're trying to predict, in this case, the price of a used car. The variable x stands for the different attributes of the car, like its age, mileage, or make. The equation shows that the predicted price y depends on a weighted combination of these attributes, plus a bias term w0. When we talk about g, x theta, that's our model, the function that takes these attributes and estimates the price, with theta representing the parameters, which are essentially the weights and biases we learn during training. This approach, called prediction by regression, is fundamental in many predictive modeling tasks. It helps us understand how each attribute influences the final prediction. So, in essence, our goal here is to find the best parameters theta that make our model's predictions as accurate as possible, connecting back to the overall theme of building effective predictive models. All right, let's dive into slide 13. Here, we see a coordinate system with variables x and y, which are essential in describing positions in a plane. The angles alpha1 and alpha2 are key components, and they are defined by the functions g1 and g2. So alpha1 equals g1 of x and y, while alpha2 equals g2 of x and y. These functions help us understand how the angles relate to the position of the car or robot arm. Speaking of a car, this slide mentions navigating a car, specifically the angle of the steering wheel, as studied in the CMU NavLab project. It's a practical example of how understanding these angles and their relationships is crucial for autonomous vehicle navigation. Next, we have the kinematics of a robot arm. As you know, kinematics deals with motion without considering forces, which is fundamental for controlling robotic systems precisely. Finally, we touch on regression applications, which involve modeling and predicting these relationships, like how the angles depend on position, using statistical methods. Overall, this slide connects the mathematics of angles and positions to real-world applications in navigation and robotics, emphasizing the importance of understanding these functions in various systems. Let's take a closer look at some examples of decision tree tools that create rules. These rules are incredibly useful because they allow us to predict future cases by applying the same logic to new data. Essentially, once we've established a rule, we can use it to forecast outcomes for inputs we haven't seen before. Another key benefit is knowledge extraction. Because these rules are straightforward and easy to understand, they help us interpret complex data in a simple way. This transparency is one of the reasons decision trees are so popular. Additionally, these rules often lead to data compression. They simplify the underlying data by capturing its main patterns, making it easier to analyze and communicate. Instead of dealing with massive datasets, we work with concise, meaningful rules. Outlier detection is another important aspect. If there are exceptions, like potential fraud cases, that don't fit the established rules, we can identify these anomalies more effectively. This makes decision trees valuable for spotting unusual or suspicious activities. Finally, all of this falls under the umbrella of supervised learning. We're using labeled data to train our models, so they learn the rules that can then be applied to predict or analyze new, unseen data. This approach is fundamental to many predictive modeling applications today. So here we're talking about learning. What normally happens through unsupervised learning? Essentially, this means discovering patterns or structures in data without any predefined labels. One key technique is clustering, which involves grouping similar instances together. For example, in customer relationship management, clustering helps segment customers based on their behaviors or preferences. Clustering isn't just limited to that. It has other practical applications too, like summarization, where it helps condense large datasets into meaningful summaries, and association analysis, which finds interesting relationships between variables. Some real-world examples include customer segmentation in CRM systems, which I mentioned, but also image compression through color quantization, reducing the number of colors in an image while preserving visual quality, and bioinformatics, where it's used to learn motifs, these recurring patterns in biological sequences. Overall, this slide highlights the versatility of unsupervised learning, particularly clustering, as a powerful tool for uncovering the normal structure in data. It's all about understanding the underlying patterns that can inform decision-making and further analysis. So let's dive into some of the core concepts behind reinforcement learning. First, we have policies, which are essentially the actions an agent should take in a given situation. Think of it as a guide for decision-making based on the current state. Then, there's utility estimation. This is about figuring out how good a particular state is, and it's what the policy relies on to make informed choices. One of the unique aspects of reinforcement learning is that there's no supervised output like in traditional supervised learning. Instead, we have delayed rewards, meaning the agent only finds out how well it did after a sequence of actions, not immediately. This leads us to the credit assignment problem, determining which actions or decisions were responsible for the eventual outcome. It's a tricky but essential part of shaping the agent's learning process. Now, these concepts open up a wide range of applications. For example, game playing, where agents learn to compete or cooperate, robots navigating through mazes or complex environments, and even scenarios involving multiple agents working together or in opposition, often with partial observability of the environment. All of these highlight how reinforcement learning models real-world decision-making processes, making it a powerful approach for autonomous systems. Now, let's take a look at some valuable resources where you can find datasets for your machine learning projects. First, we have the UCI repository, which is one of the most well-known sources for datasets across a wide range of domains. You can access it at UCI Edu and explore numerous datasets that are frequently used for research and benchmarking. Next, there's the UCI KDD archive, specifically focused on data mining and knowledge discovery tasks. It's a great resource if you're interested in data related to network intrusion detection, clickstream analysis, or other complex data mining challenges. You can find it at KDD, IKES, UCI Edu. Then we have StatLib, hosted by Carnegie Mellon University. It offers a broad collection of statistical datasets, which are particularly useful if you're working on statistical analyses or methods. The URL is stat.cmu edu. Finally, Delve is another resource worth mentioning. Hosted by the University of Toronto, it provides access to various datasets and tools for data exploration and analysis. All of these resources are excellent starting points for gathering high-quality datasets that can help you develop and evaluate your machine learning models effectively. Remember, the key to successful modeling often lies in the quality and diversity of your data, so these repositories are invaluable tools in your toolkit. Let's take a look at some of the key resources available for staying current in the field of machine learning. As you can see, there are several reputable journals that publish cutting-edge research. For instance, the Journal of Machine Learning Research, or JMLR, is one of the most well-known sources for new developments in our field. Then there's the IEEE Transactions on Neural Networks, which focuses on advancements in neural network research. Similarly, the IEEE Transactions on Pattern Analysis and Machine Intelligence covers a broad range of topics related to pattern recognition and AI. We also have the Annals of Statistics and the Journal of the American Statistical Association, which are crucial for those interested in the statistical foundations underpinning machine learning algorithms. These resources are essential for anyone wanting to deepen their understanding and stay informed about the latest breakthroughs. Overall, these journals represent the backbone of scientific communication in machine learning, providing a steady stream of innovations and insights. Staying connected to these resources helps ensure we're not only keeping up, but also contributing to the ongoing progress of the field. Let's take a quick look at some of the major conferences in the field of machine learning and artificial intelligence. First, we have the International Conference on Machine Learning, or ICML, which is one of the most prestigious gatherings for researchers and practitioners alike. Then there's the European Conference on Machine Learning, or ECML, which highlights innovative work coming from the European community. Next up is Neural Information Processing Systems, known as NIPS, a conference that covers a broad range of topics from neural networks to deep learning. Moving on, we have computational learning, which often focuses on theoretical foundations and advancements in learning algorithms. The International Joint Conference on Artificial Intelligence, or IJCAI, is another key event that brings together AI researchers from around the world to share their latest findings. Additionally, the ACM SIGKDD Conference on Knowledge Discovery and Data Mining, or KDD, is renowned for its focus on data mining and knowledge discovery techniques. Finally, there's the IEEE International Conference on Data Mining, ICDM, which further emphasizes practical applications and new developments in data analysis. All of these conferences are valuable resources for staying up to date with the latest research, networking with experts, and understanding emerging trends in our field. They play an essential role in advancing the science and application of machine learning and AI across different communities and industries. Today, I want to give you an overview of Alpidin and CH, Ike's ML Topic 1 course. This is an introductory course that covers a wide range of machine learning techniques, from the basics all the way to the most advanced, state-of-the-art methods. It's designed to give you a solid foundation across the spectrum of machine learning. The course tends to be more theoretical and statistics-oriented compared to some of the other courses I teach. That means you might need to stay engaged and do some continuous work to keep up, especially with the more complex concepts, so don't get discouraged if it feels challenging at times. What you'll learn includes many methods you've probably heard about before, like naive Bayes, belief networks, regression, and nearest neighbor methods such as KNN. You'll also explore decision trees, support vector machines, ensemble learning, and important issues like overfitting and regularization. In addition, the course covers techniques for reducing dimensionality, including PCA, and understanding error bounds, parameter estimation, and mixture models. You'll learn how to compare different models, perform density estimation, and dive into clustering techniques centered around k-means, M, and DBSCAN algorithms. We'll also touch on active learning and reinforcement learning, so you get a broad view of how these methods work and where they're applied. Throughout, the course integrates algorithms, theory, and real-world applications, making it not just about understanding concepts, but also about seeing how they work in practice. And yes, it's going to be both fun and challenging, so expect to work hard, but also enjoy the journey of mastering these techniques. In summary, this course, COSC 6342, is a comprehensive introduction to machine learning, covering the essentials, the theory, and the applications, all aimed at giving you a strong foundation for further exploration in this exciting field. All right, as we wrap up, I want to highlight some of the key points from this final slide. First, we briefly touched on graphical models and belief networks, which are powerful tools for representing complex probabilistic relationships, but unfortunately, we ran out of time to explore them in detail. Next, we looked at more on adaptive systems, emphasizing how these systems can learn and adapt over time, which is a crucial aspect of machine learning. We also discussed learning theory, which provides the foundational understanding of how and why algorithms learn from data. Then, we covered more on clustering and association analysis, which are topics that you'll find further developed in the data mining course, so those are important for discovering hidden patterns and relationships in data. We also went into more on feature selection and feature creation, highlighting how selecting the right features or creating new ones can significantly improve model performance. Prediction was another key area we touched on, underscoring its role in forecasting future data points based on learned models. Finally, we mentioned the possibility of exploring topics in more depth, like optimization techniques, neural networks, hidden Markov models, and the practical aspects of conducting machine learning experiments, including comparing different algorithms. If we had more time, these are the areas that could benefit from further coverage, giving you a broader and deeper understanding of advanced machine learning techniques and their applications. So, in summary, this slide is about recognizing the vast scope of machine learning and identifying where we might want to focus more if we had additional time. It's about deepening your understanding of these key areas to become more proficient in designing, implementing, and evaluating machine learning systems.